Good morning, honors chemistry students. The next molecule that I'd like to review with you today as part of our continuing review of molecules for the molecular geometry lab is the molecule of oxygen. Oxygen is one of the Dr. Hofbrinkel gases and has a chemical formula of O2. So it's a diatomic molecule in its free or naturally occurring state. And we refer to it as a homonuclear molecule because there are two atoms which are the same that make up the molecule. So therefore, both atoms are the same. So we refer to it as being homonuclear. The second column on your molecular geometry lab, excuse me, is going to be a column whereby you are going to have to illustrate the molecule once you make the molecule itself, once you've completed all the predictions on your paperwork. That being said, we're going to save the illustration for last. And we want to get right after what we call the AELD, or the atomic energy level diagram. For oxygen, by now you should recognize that oxygen, at least in terms of the individual atom, has an atomic number of 8, so it has 8 protons and 8 neutrons. It also has 8 electrons. The first 2 go in the first energy level and the 1s sublevel. And then it's a member of group 6A, so it has 6 valence electrons. 2 in the 2s, 1 in this 2p, 1 in that 2p, and then for right now I'm going to place this 2p in pencil and then go back and finish off the 6 valence electron there. So in essence, oxygen has a total of 6 valence electrons. That being said, we're going to show how this bonds to another oxygen atom, which also has 8 protons, 8 neutrons, and 8 electrons. The first 2 electrons go on the first energy level, and the remaining 6 go on the second. 2 in the 2s, 1 in this 2p, 1 in that 2p, and again we'll draw this one in pencil, 1 in this 2p, 1 in the final 6th one there. This is a little bit out of kilter, but we'll have to work with it. The issue that you see when you do that is the fact that when, according to the octet rule, that when atoms gain, lose, or share electrons, they try to achieve the octet state. And one can clearly see that this oxygen atom merely has 7 valence electrons, 2, 4, 6, 7. And that is also the case with this oxygen atom, which has 2, 4, 6, 7 valence electrons. So that being said, one of the strategies we have to show how oxygen bonds is to create 2 shared pairs of electrons. And we'll shore these orbitals up, hopefully. It's kind of easier to draw them the first time. So now what you see is you have an oxygen atom that's in the octet state. It has 2, 4, 6, 8 valence electrons, as does this one too. 2, 4, 6, 8. So what we essentially have formed is what we affectionately refer to as a double covalent bond for oxygen. All right. In that fashion, we want to keep that in mind when we represent the orbital notation diagram. in that we're going to go back to our knowledge of atomic structure and quantum mechanics to represent oxygen from a quantum mechanical view. So we know that oxygen has 8 electrons, 6 of which are valence electrons located on the 2s and 2p sublevels. So there's the first 2, 3, 4, 5, 6, 7, 8. Right? So you can clearly see why oxygen's in group 6 with 6 valence electrons. We're going to bond that with a neighboring oxygen. And again, we're going to go up, down, 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 up. And we can clearly see that we have 2 unpaired valence electrons, one of which is this 2p, orbital overlap, and another one right there, okay? All right, so that being said, keep in mind always as we do these diagrams that each individual oxygen atom has 2 lone pairs and 2 bonded pairs. All right, so let's move forward to the structural formula. No, excuse me. Let's move forward to the electron-dot notation. So you should be mindful of the fact that in the electron-dot notation, we're only seeking to represent the valence electrons for each oxygen. So we've got oxygen on the left with 1, 2, 3, 1, 2, 3, 4, 5, I should say, 6 valence electrons. And we're going to place another oxygen atom here with 1, 2, 3. And for right now, I'm going to put 4, 5, and 6 valence electrons. Once again, you see we have that situation where neither oxygen atom is in the octet state because this has 2, 4, 6, 7 valence electrons, as does this oxygen, which has 2, 4, 6, 7 valence electrons. So the remedy for that is to form a double covalent bond. So we're going to erase this X as best we can, get rid of that puppy, and we're going to put one right here. And then we're going to erase these 2 valence electrons, and we're going to form a second shared pair there and there. So now we have represented a double covalent bond. So from each oxygen's perspective, let me slide this in. This oxygen now has 2, 4, 6, 8 valence electrons, as does the oxygen atom on the left. It has 2, 4, 6, 8 valence electrons. So they're both in the octet state. When atoms gain, lose, or share electrons, they try to achieve the octet state. So in this case, since both oxygens are nonmetals, they try to share electrons to achieve the octet state. So the next representation we're going to do is the structural formula. And the structural formula simply represents the shared pairs of electrons between the atoms with no lone pairs of electrons represented. So from this standpoint, we want to validate that oxygen has 2 valence electrons. So we're going to, has 2 covalent bonds. So we're going to have electrons in the system. We want to do an accounting of the total electrons in the system. You can either go total electrons or valence electrons, and we're going to go valence electrons because you can see that each oxygen atom has 6 valence electrons, 6 and 6 is 12. So we have 12 valence electrons in our system. However, to achieve stability in the form of the octet state, each oxygen needs a total of 8 electrons, correct? We've already been through that, but we'll show that one more time. Each oxygen needs 8, right? 2, 4, 6, 8. So 8 and 8 is 16. So our system has 12 electrons, but it needs to make the 12 look like 16. So the way it does that is to form 2 shared pairs of electrons. And when it does that, 16 minus 12 divided by 2, that means there are 4 electrons that have to be involved in bonds, which we can clearly represent. 4 divided by 2 is 2, right? All right, very good, because there are 2 electrons per bond. The next representation that I want you to diagram is the Lewis-dot diagram, which is really a hybrid of these two diagrams, the structural formula and electron dot, because you have a double covalent bond between the oxygens, and you have to represent the lone pairs for each oxygen atom. So there's your Lewis structure. And the Lewis structure, it represents shared pairs of electrons with a line and lone pairs as such. All right, so we go from Lewis dot structure to bond type. And in the bond type, we're looking at the electronegativity differences between each of the atoms. So we know the electronegativity of oxygen is 3.5. You may get different values, but it should be, depending upon which periodic table or source you use, but it should be pretty close to that. The difference between those is 0.0, which, if you remember, there's a sliding scale that between 0.0 and 0.4, an electronegativity difference between 2 atoms in that zone is identified as being nonpolar covalent. If it's between 0.5 and 1.7, electronegativity difference, the bond is identified as being polar covalent. And if it's from 1.8 or greater, it's identified as being ionic. So since 0.0 is at the bottom end of this range, we'd say it's nonpolar covalent. And the significance of that is what that tells a chemist is the electrons involved in the bonds between the oxygen atoms are shared equally. So there's no net separation of charge between the 2 atoms. All right, so the bond between the oxygens is non-polar. So that being said, we want to do a calculation to predict the geometry of the arrangement of those electron pairs around each oxygen atom. Typically, we do this calculation on a central atom, but since we only have 2 atoms, we don't have a central atom. So we're going to examine the arrangement of the electron pairs around each individual atom. So it goes something like this. Each oxygen has 2 lone pairs and 2 bonded pairs, but in the VSEPR system, multiple bonds count as 1 bonded pair, because whether you have 1 or 3 bonds between the oxygen atoms, they're fixed in space. So 1 and 2, 1 plus 2 is 3, and 3 total pairs predicts a trigonal planar geometry. How do we know that? You have to memorize that, because that's what theory says. So theory says when you draw your valence shell electron pair repulsion theory diagram, that the arrangement of those electron pairs is going to be in a trigonal planar arrangement, something like this, where you have 2 oxygens bonded together and the lone pairs are held at bond angles of 120 degrees to create a trigonal planar arrangement where all three of those electron pairs, whether it's bonded or lone, are in the same plane. In this case, the plane of the paper, and they repel themselves to positions of minimum repulsion. Keep in mind that the electron pairs, whether they be bonded or lone, all have negative charges. Similar charges repel, so theory says they repel themselves to bond angles to minimize the repulsive forces between them. So we're going to say that this is a trigonal planar arrangement, and the electrons are held at 120-degree bond angles. VSEPR theory is developed, or VSEPR theory, valence shell electron pair repulsion theory, is developed according to the localized electron model of the atom, and really seeks to explain the arrangement of the electron pairs around an individual atom when it's not bonded. But to explain the arrangement of electron pairs around atoms when they are bonded, scientists or chemists came up with a companion theory known as hybridization theory. And in this case, what hybridization theory seeks to explain is, or to explain, hybridization theory seeks to explain the behavior of electrons when they bond in a molecule. So theory says to explain the arrangement of electron pairs so that there's one bonded pair and two lone pairs, there's an overlap of an s orbital with two p orbitals to create what we call as sp2 hybridization, which leaves three equivalent hybridized orbitals that are bonding. So the way this is kind of explained is to draw two oxygen. Ooh, I almost blew it right there. Wow. We'll do this one at a time. Is to have three equivalent sp2 hybridized orbitals. Almost blew that. That's a save. Here's another one. Here's another one. So there's your three hybridized orbitals. And then this oxygen also has three hybridized orbitals. Whew. Almost had a brain infarct there. All right. And in these unhybridized orbitals, we're going to place one lone pair there, one lone pair here. And this is going to be hard to see by the way I drew that. I'm so sorry. You're going to have one arrow going up and one arrow going down. And then you're going to have one up, one down, one up, one down there. So this should be one arrow going up and one arrow going down. So that's beautiful. But the problem we have with doing this is you notice that if you assign electrons to each oxygen atom, this one would have 2, 4, 5, and this one would have 2, 4, 5. But we actually need 6 valence electrons for each oxygen atom. So where are the remaining 2 electrons? One for each oxygen atom. Well, you notice up here that one of the orbitals is unhybridized. So theory says there's an unhybridized orbital right here and an accompanying one right here. Okay? And that accompanying one, in each one, you have electrons of opposite spins. And we say that these can form a second bond, which is referred to as a pi bond. The first bond is always a sigma bond. I'll write those words over here. The first bond is a sigma, and the second bond is known as a pi bond. The sigma bonds are formed from direct overlap of orbitals. The pi bonds are formed from indirect overlap of orbitals. So in any multiple bond system, the first bond is always going to be a sigma. The remaining bonds are always going to be pi bonds. And again, you see that the 120-degree bond angle is evidenced. We say that the geometry is trigonal planar, and we say that the hybridization scheme is sp2. Not sp squared, but sp2. So that's all beautiful. But in the end, what we're interested in is the actual geometry, not just the predicted geometry. So in the actual geometry, we cover up lone pairs and only look at bonded pairs. So theory says that we're only going to look at the bonded pairs, not the lone pairs. And again, 2 points clearly form a straight line with a bond angle of 180 degrees. And we say that the actual geometry of the oxygen molecule is linear, which is true of all the homonuclear diatomic molecules that make up the Dr. Hofbrinkel gases: hydrogen, oxygen, fluorine, Hofbrinkel, right? Bromine, iodine, nitrogen, and chlorine. They're all diatomic molecules with a 180-degree bond angle. I also want you to write the bond energy. Look that up. And you'll find that the bond energy for oxygen is 495 kilojoules per mole. You can get that from a table in the book. Those values may vary, but they should be relatively consistent. And I also want you to look up the bond length, which in this case I believe was 1.41 picometers, if memory serves me correct. Or is it 141 picometers? Got to check that value. But nevertheless, I want you to look it up. I'm thinking it's 141. Okay, so I'll provide clarity in class on that. And the last two columns are the AXE column, which really is designed to look at the number of bonded pairs and lone pairs in a central molecule, or in a central atom in a molecule. But for this, we're just going to write AA, since both the atoms are the same. A represents the central atom, okay? And we don't really have a central atom. We have two atoms side by side. And then last but not least, here, I almost did it. We want to note the polarity of the molecule. All right, so since you have electrons that are shared equally between the two atoms, we're going to refer to this bond as being nonpolar, and so thus the molecule itself is nonpolar. Okay, so the bond is nonpolar covalent, as we've already noted, and the molecule is nonpolar. So all that being said, that is the molecular geometry of oxygen. The next molecule we're going to look at is hydrogen fluoride.